recording so that nobody misses the content of the lecture. Okay, here we go. So, with electric fields, the electric force, the thing that sort of drove that was electric charge, right? So, in fact, if we even go back further, we had gravity was due to mass. Electricity was due to charge. And now we have magnetism, which is actually, the definition of magnetism is actually pretty weird, but it's really due to moving charge. Turns out that electricity and magnetism were the first two fundamental forces to be unified. I think back in the 1800s is when they were unified into the EM force. So I guess really the central point behind this for physics is that electricity and magnetism are caused by the same thing. You just have to have a different perspective on it. So a moving electric charge will cause a magnetic field. That's how it arises. Let's break down magnetic fields, though, to our most simplest of possible forms. Let's say we have a bar magnet, right? Gosh, and this is where I really wish we could be in classroom. In our actual classroom, because I have bar magnets I could show you. They have a north and a south pole. And kind of like charges, if you have another magnet, right, with a north and a south pole, the north poles are going to repel each other, and south poles are going to repel each other, and then the opposite ones are going to attract. Very much like charges. Well, I lost my notes. Hold on. There we go. Okay. One of the weird things about magnetic poles, though, is that you can't separate them. If you took a bar magnet like this and you chopped it in half right down the middle, you wouldn't get a north pole and a south pole just by themselves. You'd get two little magnets, each with their own north and south poles. And even more than that, they'd have about half the field strength of the original magnet each. So the total field strength would stay about the same. And you can keep chopping these in half, right? All the way down to the molecular level, or even the atomic level. And you'll get a single atom with an electron, which has itself a north and a south pole. And then if you take this atom apart, you're not going to have a magnet anymore. It won't really work. So magnets are kind of weirdly indivisible. You can't get what's called a monopole. So magnetic monopoles are actually there's no physics reason they can't exist. As far as we know, nothing in physics says that you can't have a magnetic monopole out there somewhere. It's totally possible that some weird particle we've never seen before, has the property that it is just like a north pole of a magnet. But it has never been observed in nature. And it's kind of become one of the rules of magnetism that it's not that you can't have them, but you just don't have them. It's pretty odd. I guess it's one of the big mysteries is why are there no magnetic monopoles? Very recently, in the last couple of years, some scientists, some physicists in labs have constructed very small, microscopic groups of particles that act as if they were a magnetic monopole under very particular circumstances, which is kind of cool. If magnetic monopoles existed, a lot of really cool stuff could also exist, like hoverboards, really cheap maglev trains, things like that. They'd be very useful, to say the least. So yeah, magnetic monopoles. Unfortunately, we cannot have them. So what we do have is magnetic dipoles with a north and a south pole. It's like up here. I'm going to draw another one down here so I can draw field lines. So magnetic field lines are a lot like electric field lines. They have a lot of the similar properties, but not exactly the same. Gosh, I lost my notes again. There they are. So the strength of the magnetic field is proportional to the density of field lines, just like with the electric field we had. All magnetic field lines are closed loops, very much unlike electric field lines. So if I say north and south here, a magnetic field is going to come out of the North Pole and go into the South Pole and make a complete loop like that. You might remember for electric fields, if I had a plus, the electric field was going to end on that object. Right? Like the actual field line ends on the surface of the positively charged thing. Whereas for magnetic fields, it actually goes through the magnetic thing and it's continuous and unbroken. Maybe on the other side you'd have another kind of loop that circulates counter to that. Like that. And you can imagine this is actually a 3D thing, so it's kind of like a donut. You have a bunch of magnetic field lines going up through the middle, and then they're all going down on the outside. It's weird for me to say down when I'm actually meaning right, and up when I mean left. I guess that's just the way I think about it. Let's see. Oh, one little thing about these guys I forgot is that the way to think about bar magnets or any real physical magnet is what they call domains. Domains are like little groups of particles, or maybe even single particles, if you get really down to it, that each are themselves tiny magnets inside of the big magnet. So in a regular ferromagnetic bar magnet, most of the domains are going to have their north-south poles aligned with the north-south pole of the big magnet, but some of them are going to be a little bit off, maybe. And the average sum of all the north-south pole vectors is going to be equal to the big one. So really, you can think about domains as like little micromagnets that add up to the big magnet. You can have all sorts of different types of magnets. So there's ferromagnetism, where almost all the domains are lined up parallel north-south in the material. There's ferrimagnetism, which is they're a little bit less aligned. They're sort of aligned, but not all fully going in the same direction. There's I'm struggling to remember. I didn't write it down in my notes. It's called, I think it's paramagnetism, where all the domains are aligned parallel to some external field, magnetic field. So if you stick like a bar of metal into some strong magnetic field, they're going to maybe align with that field. Then there's diamagnetism, which is, I think, perpendicular to some external magnetic field. There's all sorts of types, and I honestly do not remember what all of them are. It's not incredibly important. But there's all sorts of types that have to do with what the domains inside of the magnet are actually doing. I'm going to write that word down here. There you go. Yeah, okay. Any questions about the sort of more qualitative side of magnetism that we're talking about? Otherwise, I'm going to start going into more mathy stuff. Mm. Oh, and I guess... Say what again? Domains? I guess you could say about domains that, like, on the really smallest level... Oh, a lot of questions. I'm going to try to get to all of them. Domains. On the really smallest level, you could say domains are like the alignment of electron orbits. So remember how up here I was defining magnetism as a moving charge? So if an electron is orbiting around the center of an atom, right? That's a moving charge and it's creating magnetic field. So at the very smallest, like microscopic sense, you could think of domains as the alignments of the magnetic fields of individual electron orbits. And if you have all those orbits aligned in a material, like pretty close to aligned in the same direction, then you'll have a good ferromagnet that you know, like a good bar magnet. Could you have a agnet that had different masses for its poles? Oh, a magnet that had different masses? Yes, you could absolutely have a magnet that had different masses for its poles. You could have one that's like, I don't know, like a big boy, little boy. And you could have a north and a south pole, maybe. But the thing is, if you chop that in half, you know, this big chunk would have a north and a south pole all by itself, and the little chunk would also have a north and a south pole all by itself. Other questions? Wait a minute for other questions. I'm going to start a new document, though. What do the fields look like when they interact? Ooh, that's a really good question. I was hoping you guys wouldn't ask that, because it's really difficult. So one of the rules about magnetic field lines is that they can't cross each other. So if you had like a magnet with field lines like this, kind of like a bar magnet, circulating around like that, and you have another magnet come close to it, right? The field lines are not going to intersect or like cross each other. They're going to squish, and they're going to do... man, it's really hard to draw. They're going to like squish together and get denser, like closer together, but they're not going to cross each other. It's kind of one of the rules about magnetic field lines, is that they can never cross. And I guess one of the reasons for that is that if you had two field lines crossing each other, then at one point, the point where they cross, then the value of the magnetic field would have actually two values, right? It can't be a two-valued function at one point. It has to have a single value at a single place in space. So unfortunately, that means field lines can never cross. It's a really good question, and I wish I had a better answer for it. Any other questions before we move on to the more numbery stuff? Isabel, did I get what you needed to write down? All right, I'm going to move on. Okay, so weirdly, you would think the magnetic field, like the letter for it would be M, but of course not. This is physics. We have to be complicated. So we use B for the magnetic field. I thought about taking some time to teach you guys some of the formulas for magnetic fields. So unfortunately, there's no like set formula for magnetic field like there is for an electric field. There's a bunch of different ones. So, for example, for the magnetic field from a current-carrying wire, there's one particular formula. For a current-carrying loop, there's a different formula. Based on the shape, like the geometry of the magnetic field, there's all sorts of different formulas. Then I decided it's actually not really worth it for us to go over what all those individual formulas are. You need to derive them using three-dimensional calculus, and we're just not ready for that, most of us. That's a college kind of thing. So, when I'm referring to magnetic fields, it'll just be like giving you a number. The units. Good question, because that's literally the next line in my notes. The units of a magnetic field are either Tesla, T, or Gauss. I think it's just G. 1 Tesla is way bigger than a Gauss. 1 Tesla is 10,000 Gauss. Most of the magnetic fields we deal with on a daily basis are very small. So we're talking about Gauss, but I think Tesla is the standard unit. And in fact, I looked up a table of magnetic fields here. This is one of my favorite physics websites, physics.info. If you ever want to visit it, it's super awesome. It doesn't have everything, but it has so much, and it has really good practice problems too. So here are some sample magnetic fields. B, in Tesla, the theoretical upper limit of a magnetic field is 10 to the 13 Tesla from a neutron star. And you have, really ridiculously high magnetic field. And then we drop a lot, down to 1,000 Tesla is the highest laboratory field ever produced. As of this writing, I don't know when this was written, probably a few years ago at least. Highest laboratory field sustained is 45 Tesla. A field strong enough to levitate frogs, 16 Tesla. I found the video of that. And don't worry, the frog was fine. I would say default to Tesla. Unless I ask you otherwise, I would default to Tesla. Frog time. Don't worry, no frogs were harmed in the making of this physics. They were levitated, though. There he is. Frog levitated by magnetism. It's a 16 Tesla magnetic field, which is kind of crazy. Everything is magnetic as long as you try hard enough, I guess. It's the idea. Because everything has, electric charges in it. Oh, is that a cricket? Crazy. Yeah. Levitating a cricket. Anyway, I thought you guys would enjoy videos of levitating frogs. Levitating flowers? That's new. A lot. It would take so much. Because, you know how big a cricket is, right? It's a teeny boy. You need a really huge magnetic field to levitate a human. So yeah, strongest superconducting magnet is 13 Tesla. Strongest permanent magnet. What if we used a child? Okay, yeah, sure. I think the strongest magnet that I have interacted with was a huge electromagnet in my college lab, and it was, I think, it was somewhere over 2 Tesla. We think it was around 3 Tesla. But we couldn't be sure because every meter we had was basically pegged by this thing. It wouldn't. It would go to the maximum amount of the meter, and none of our meters could measure magnetic fields that big. So we think it had about 3 Tesla field, but nobody could actually verify that because no instrument was measuring. No instrument we had in the physics lab would measure a magnetic field that big. MRIs are pretty darn strong, 1 to 4 Teslas. New method project. Oh god. I like that idea, but I'm also kind of disturbed. Um, 0.45 Tesla for a really large sunspot. At the poles of a good iron bar magnet, we're talking 0.15 Tesla. Your standard refrigerator magnets are 0.1 Tesla. The sun's magnetic field is 0.001 Tesla at its poles, which is, like, should be, I hope, surprisingly small. Oh, for an MRI, 1 to 4? I would say there's just different models of MRI machines. And, they're doing different things. So, probably, like, the really strong ones are, I would guess, used for really deep scans, whereas the weaker ones are used for shallower scans. I'm sure it's variable. Like these magnetic field strengths for planets and even the sun are like really small. Like we're talking like 60 millionths of a Tesla, right? Or like a few Gauss. Yeah. Let's see. The human brain, 100 times 10 to the minus 15. I don't know why they just didn't say 10 to the minus 13, but that's that. But there is a magnetic field inside our heads. So, yeah, there you go. I don't think you're going to have to memorize any of these. I know you're not going to have to memorize any of these. If you need to look them up, it is on physics.info/magnetism, which is it's a whole lecture, basically, about the history of magnetism and all that. And then it's got some more stuff in it. But which of you do I think has the strongest magnetic field in your heart? I don't know. Definitely not Jacob. Let's get back to the actual physics. Where the heck was I? Oh yeah. Okay. I wanted to show you the force law for magnetism. It's called the Lorentz law. Lorentz force law. It's pretty simple. The magnetic force, and I'm using a B for magnetism again, is this is the magnetic force on a charge moving through a magnetic field. It's the charge times the velocity of that charge, which is a vector, times the magnetic field. And here's the really interesting thing about this guy right here. So my question to you guys is, how do you, so say maybe my V looks like that and my B looks like that. How do I multiply directions? Oh my God, it's like Prince Victoria. You're so right. Oh God, how do you spell your name? The sign says which way and regular multiple. Don't know what that means. I always panic when have to name. Wow, some interesting stuff going on in that chat. So the what's going on here is a special kind of multiplication called a cross product. So this is going to be really important for problem 1 from the homework. Everyone, I can't see you, but get your right hand out. Get it out. Take it out. Right hand. This is called the right hand rule. I'm going to wait till you all have it out. Okay, right hands are out. I'm going to assume your right hand is out. If the magnetic field, B, is pointing in the direction of your pointer finger, and the velocity, v, is pointing in the direction of your thumb, then your palm going up, or your middle finger going straight up, is the direction of the magnetic force. This is the result of a cross product, where you have v and b, two vectors, and then the result of multiplying them with a cross product is a third vector that's going perpendicular to both of those original vectors. So in this case, so if I say b that I've drawn here, b is going that way, and v is going that way, the perpendicular vector is going straight into my screen. So the direction of force is going into the screen. The way I would draw that here is I would draw a circle and an X for the force. And what that's supposed to represent an arrow, right? So the magnetic field going into and out of, or any vector going into and out of the page or the screen is supposed to represent an arrow. If it's going into the page, what you're supposed to draw is the fletchings on the back of the arrow. And if it's going out of the page, you're supposed to draw a circle with a dot in the middle, which is, I guess, supposed to represent the arrowhead. So that's pretty critical to understand how to do problem 1 from the homework. And all of problem 1 is doing is applying this right-hand rule. So remember, B field is pointer finger, velocity is thumb, and middle finger coming out of your palm is the force. That's all that problem is just applying that a couple of times. If you want to do some math with the field, we're going to simplify this. So, why the right hand? It's convention. It's just the way that we decided it works. The reason it's the right-hand rule at the root of it is that Benjamin Franklin decided that positive charges were positive and negative charges were negative, and that current flowed from positive to negative in a circuit. Remember when I was talking about that, was it last week? If he had decided actually correctly that actual charges are flowing from negative to positive, we'd be using the left-hand rule. It's related to the direction of current. So there's no real reason. You could do both, or you could do either for physics, and you'd get the right answers as long as you're starting from the right point of like how you're defining current. But in the way that we have defined physics for the last 300 years, we need to use right-hand rule. Okay, where was I? I was at the equation. So if V and B are perpendicular, if they are at right angles to each other, which can happen in plenty of circumstances, this cross product actually just, V is the velocity of the charged particle. The cross product just collapses into regular multiplication. So Q times V times B. That gets you the magnitude of the force. If they're not perpendicular, it's not this. There's like I think it's a cosine. I think it's a cosine theta in between, but I can't quite remember. And do remember the direction of this force is still going to be, right, BV in this case, going into the screen. So if you want to just calculate the magnitude of the magnetic force, if it's perpendicular, I'll write that down. Here's your equation. What? My pen's doing weird things. And what's Q? Q is the charge of whatever particle is in there. So like an electron charge, an elementary charge probably. In fact, in our homework, that is what it is. It's an electron. I think the homework says a cosmic ray electron, so it's just an electron. So it'll be the charge, like the elementary charge of an electron is all it is. Let me look at my notes. What else do we have to look over? Oh, for problem 12. For problem 12, it actually asks you what the radius is of the circle that the particle makes. So what really is going on, let's say you have, I don't know. Let's say you have a magnetic field coming out of the screen. And you have a particle moving up through it. So B is going that way, V is going that way. So the force on this particle is going to be, another color. Is going to be initially, the force is going to be like this. But then the particle's path is going to start curving because the force is being applied to it. And in fact, it'll actually make a circle eventually. To figure out the radius of that circle, we're going to need to use centripetal force, which you may or may not remember from Physics 1. But essentially, we're going to set this QVB, the magnetic force, equal to the centripetal force, which is mv squared over r. And I think in this case it's an electron, so the mass of an electron, charge of an electron. The velocity I think is given, the b I'm pretty sure is given, and then v there. So solving for r, mv squared over qvb, so the v's are going to cancel, so you're going to get mv over qb. So that's how you'd find the radius of the circle that the path of the electron makes. Is it sine theta? I thought I didn't remember it correctly. I believe you. That makes more sense. Anyway, that's how you do that problem 12 from the homework. And the homework is only that. It's problem 1 from the online textbook and problem 12 from the online textbook. Problem 1 is basically a bunch of diagrams like this guy down here in the left corner that show like the velocity of a particle and the magnetic field, and you have to figure out what direction the force is going, which is just applying the right-hand rule. I think there's 6 of them you have to do. And then problem 12 is just a single application of this, setting the magnetic force equal to the centripetal force. And that's all the homework really is. That's all I wanted to get through this week. Whew! How you guys feel? That was a lot of information to throw at you in more time than I thought. 45 minutes. I thought it was like 15 minutes. Oh, gotta stretch. Oh. Let's go magnets. Yeah. Whew. There's a lot of information. Questions, comments, lament, sadness. Can I now teach you quantum physics? No. It would take me a little while to get prepared to teach quantum physics. I haven't taken any quantum physics since I was in college. If you want to see some of it, maybe I can work some up for after the seniors are gone, but it's going to take me a little while to get back into it.